Okay. So hi everyone. Today I wanted to talk about one example that sort of helps to understand a more general setting of topoi. Well, at least in the case of lower topoi, so just sheaf topoi, where we consider sheaf of sets. So this is closely related to general topology, localic, stuff like that. So basically, today it will be somewhat informal talk, but I'll try to prove a couple of things, and I hope that we will see some interesting examples of this fairly abstract formalism that we can apply to some very, very concrete things. Okay, so let's start. So first question is obviously why we want to replace topological spaces by anything. After all, topological spaces are so intuitive. And the answer is quite simple, because actually when we do various constructions involving sheaves, and to be fair, most constructions in general with topological spaces, we don't really need the fact that topological space consists of points. What we really need from topological space is some kind of a category, in particular, a category of open sets. So I denote by this curly category of open sets. And since our passage to the sheaf category on topological space goes through this category, it means that we don't actually need topological spaces. We can start from some axiomatic definition of such a category and then consider sheaves of it. That's the basic idea behind pointless topology. So instead of a space consisting of points, we just consider an abstract category of open sets. Okay, so as I said, an idea of local goes like this. So we want to find some set of axioms for a category of open sets of a topological space. And basically, we already know what axioms we need from point set topology. So as we know, the topology on topological space must contain arbitrary unions of open subsets. So that's the first natural axiom. Then we know that finite intersections of open subsets are also open. So that's another axiom. And also we have one more axiom, which is a little less, I guess, well-known than the previous two. But nevertheless, we should have this distributivity law that says that we can distribute arbitrary unions over finite meets from finite intersections. So abstractly, this category of open subsets of a topological space with the relation of inclusion forms a lattice, meaning that we have finite joins and meets, where meets and joins are just special kinds of limits and colimits. And actually, we require one more property from this lattice. In particular, we require to have this infinite distributivity law. We say that infinite meets distribute over finite joins. So that's all we need. That's basically the definition of a frame. So frame is this kind of abstract category of open subsets. Yeah, so we take a pole set. We're required to have finite meets, arbitrary joins, and infinite distributivity law. And then we say that such a category is called a frame. by definition, any frame has a minimal element and a maximal element. So a minimal element is just a join of an empty family, and the maximal element is just the meet of an empty family. So obviously this corresponds in a topological setting to an open subset and the whole space. Okay. So now when we define some objects, it's natural to ask for morphisms between them. And we basically, once again, use our intuition from topological spaces. We say that a functor between both sets is called a morphism of frames, if finite meets compute with this functor, and arbitrary joins also compute with this functor. So once again, we can think of it as just something that is induced by a continuous map on categories of open subsets. So obviously, if we have a continuous map, then we have a pre-image functor on categories of open subsets, and it is quite clear that such a functor satisfies these two axioms. Okay, so now we can define a notion of a generalized topological space. So if a frame is like a category of open subsets, it should correspond to some kind of a space. Well, we don't know what it looks like, but we can just formally take the opposite category of frames. So the category of localics is just the opposite category of frames, formally. And we denote this equivalence between the opposite category of frames and the category of localics by these two functors. So this is the category of open subsets, so to speak, and this is just the formal functor which associates to a frame its formal dual. Okay. So obviously we have the main example, the one we derived all this from. And that's a category of open subsets of a topological space. So if X is a topological space, we can take its category of open subsets, it is a frame. And that's one reason for using this formalism. And one may ask, why even bother? Because we already have a language of topological spaces. And if we don't have any more examples, then maybe it's just stupid. We don't need this formalism. But as it turns out, actually, it is possible to define other examples of these generalized spaces. For example, there's something called measurable locales. This idea goes back to, well, I can't really say that it goes back very far, but it's an idea of Dmitry Pavlov. And the idea is that, well, right now it's too difficult to define. I don't think that we will talk about this very much, but still I need to give another example, otherwise all this is unjustified. So I'll try to give this example in broad strokes. So we can think of measurable locales as duals to commutative von Neumann algebras. So von Neumann algebras are just some special kind of operator algebras. So we can think of like some subalgebra of bounded operators in a Hilbert space. And the thing about this concept is that they're good for doing measure theory, abstractly avoiding the language of sigma algebras. So that's another possible application, although I won't go into too much detail here. But the important thing is that we can apply this language to something other than topological spaces. It's not just reformulating everything about topological spaces in some different terms and then saying that that's a great achievement. No, there are other important examples which use this formalism. Okay. So now we define morphisms of frames. And as it turns out, any morphism of frames has a right adjoint. So if phi is a morphism of frames, then we have a psi which has its right adjoint. And that's basically the way that we can pull back and push forward open subsets if we think back to this analogy with topological spaces. So how do we build this psi? Well, if we just forget everything, then we have this uniform technology to construct adjoints. We can take Khan extensions and compute them using certain coins.
Sorry, phi is an arbitrary factor.
It's a morphism of frames.
It's a morphism of frames, and for this morphism, there exists
an adjoint, yeah. But
okay.
the fact is that this adjoint is not necessarily a morphism of frames; it's just a morphism of pose sets. So yeah, thank you for this question. It's really important to note that this is an adjoint in the category of functors between abstract categories, if you want to. So psi is not necessarily a morphism of frames itself. Although phi is by definition a morphism of frames, psi may not be a morphism of frames. Yeah, thank you. That's a very insightful comment. So yeah, we have this general technology that we can take an extension, take a point, and compute it pointwise. But in the case of morphisms of frames, we have a very concrete way of doing this. So let's start from the assumption that we have some adjoint functor psi. Then the fact that it is an adjoint functor for both sets reduces to this equivalence. So we have a unique morphism from V to psi of U, if and only if phi of V maps in, well, we have a unique morphism into U. That's just the adjunction. Then we can try to apply this coin formula, and in the case of both sets, it reduces to this nice expression. We just take all V's inside of B such that phi of V is, well, we have a morphism from phi of V to U, and we take the join of all such elements. Then we claim that this is precisely the value on U. And obviously you can use this general machinery. You can see that this is precisely the, I guess, and that computes this is precisely the end that computes, well, I want to say a point that computes this adjoint. But also you can do it by hand. So assume that you have a V, which maps into psi of U. Then by construction, it is implied by this relation. So I guess I should have said it in a different order. Assume that phi of V is less than or equal to U. Then necessarily by construction, V will be contained inside of this thing, meaning that it's less or equal to psi of u. And the converse also holds. So assume that we have this relation, then V is contained in a join of some elements of B such that phi of W is less than equal to U for all elements of this join, which immediately implies that phi of V is less than or equal to phi of the join of W. Then we can use the fact that joins compute with morphisms of frames by definition. And this means that phi of V is less than or equal to U. That's precisely what we needed. So another nice thing about this formalism is that it allows to see some categorical results in very concrete setting where you can write down all these formulas with colimit scan extensions and stuff like that, just in terms of pole sets. So in terms of morphisms of pole sets, and it drastically simplifies everything, and you get these nice formulas. Okay, and I guess I should remark that if we consider a morphism of frames which comes from a map of topological spaces, so B to A, so assume that this thing was O of Y, this was O of X, then phi is just F minus 1 of for some continuous map from X to Y. And this adjoint is something that is usually denoted by this lower star. And basically it works like it's written here. So you take all open subsets inside of Y such that their preimage is contained inside of U, and then you take the union. So you try to approximate your subset from the inside. And then you take the union of all such subsets, and you get the push forward of this subset. So this construction is the basis for pull back and push forward of sheaves on topological spaces. So if you want to pull back a sheaf, you take a value on the preimage, and if you want to push forward, you basically apply this operation and then take the value. So yeah, that's another relation to some classical construction from algebraic geometry. Okay, so now we can talk about points. Although the topology is pointless, we still have points, because being pointless doesn't mean that we don't consider points. It just means that we don't give them as much credit as the point set topology does. So for us, points are just some specific kind of a morphism, but it doesn't mean that our space is completely defined by its set of points. And that's quite natural. If you think, I don't know, scheme theoretically, then it's natural to view spaces not as sets of points, but rather as some abstract objects to which we can map and from which we can map. So yeah, we have this idea. And we start by denoting with this strange looking one, the terminal locale in the category of locales. So how this works? Well, we just take the frame which corresponds to two elements. We have the initial and the terminal objects only, and we take the formal dual, and we obtain this terminal locale. And then point of a local x is just a morphism from this terminal local to x. Or equivalently, we can consider it as a morphism of frames. So we normalize, we take the corresponding frame and we map into this this minimal frame. So for frames, this will be an initial frame. And a point can be defined using another terminology. So we can define it using the so-called kernel of a point. So assume that we have a point like this, then it corresponds to a morphism of frames like this. And then we can define the kernel of this map, which consists just of an open subsets which are sent to the empty subset of, well, to the empty element of this frame. So we can actually axiomatize the properties of such a thing. So instead of a morphism, we'll just consider some specific kind of a subset inside of this frame. And we require several things. So first of all, the maximal element is not inside of K. That's quite natural because the morphism of frames naturally preserves the maximal element, since it commutes with meets and joins, and it should naturally preserve minimal and maximal elements. So first of all, this means that we can have 1 inside of K. And also, another axiom states that if a meet of 2 elements is in K, then either U is in K or V is in K. And additionally, that if some meet is in K, this means that all of its elements should also be in K. Okay. So in a sense, this definition of a kernel looks suspiciously like a definition of an ideal. And in a sense, it is an ideal. It is a proper ideal inside of a semigroup or even a monoid given by this frame and operation of taking meet of 2 elements. But we can go even. Yeah.
Two-sided ideal. Yes.
Well, since we're in a commutative setting, it's
oh, okay.
Yeah, but yeah, in general, yes. So, but we can go even further and formalize this intuition about ideals using this construction. So, formally speaking, K is just a subset inside of a frame. It's not an element of a frame, because for it to be an ideal, we sort of need to be able to. Well, I guess in a sense, it can be considered an ideal. But nevertheless, we can formulate another similar notion, which is equivalent to the notion of a kernel, and that is the notion of a prime element inside of a local or a frame. So assume that we have a kernel, meaning that we have this kind of subset which satisfies these 3 conditions. Then we can associate to it an element of the frame that is defined like this. So we just take all elements of K and we take their join. Then we have the following property. So an element is a subset of P if and only if V belongs to K. That's just it follows from property number 3, because obviously, if V is less than or equal to P, then we can add it to this union, and then we will obtain then the to this join. The join will not change because V is less than or equal to P. But on the other hand, by property number 3, this join belongs to K, which means that V should also belong to K, once again by property number 3. So yeah, we have this. And we can say that K can be obtained from P by taking an operation of downward closure of P. In just plain language, that means that we add, that we take the collection of all elements of this frame which are less than or equal to P. So in a sense, I guess there is some term for it other than downward closure, something like an ideal generated by P, or something like that. I don't know. I'm not a great specialist in theory of pole sets, but I'm pretty sure that there is a term for this operation. Okay. So we arrived to 3 equivalent notions of a point and a locale. The first one is a morphism from this terminal locale into X. Another one is a notion of a kernel, and the final one is a notion of a prime element of a locale, which is just, as promised, a proper ideal of this monoid. So it's a monoid, and the notion of an ideal makes sense since it's commutative. Yeah, it's automatically a two-sided. Okay. So how do we prove this statement? Well, I'm not going to precisely prove it, but at least I'll just sketch how to pass from one description to the other. So obviously, if we have a point, then the kernel corresponding to this point can be taken by taking the kernel. So using this definition that we had here, we take all elements such that they're mapped into the empty element of the initial frame. If we have an abstract kernel, then we can take this construction of a join over all elements of K and obtain an element of the frame which corresponds to this kernel. And finally, to retrieve this kernel from such an element, we just take the downward closure. So now if we have a topological space, then we can relate the points of this topological space with points of the corresponding locale. So if we have a genuine point in this topological space, then we can associate to it a kernel which is defined like this. So we just take all open subsets that do not contain S. So P corresponding to this kernel can be defined alternatively instead of union or join by taking the complement of the closure of this point inside of S. And obviously, we also have this map from locale or from the frame of this topological space into the initial frame, which is just a frame of a point, of a one-point space. And now we arrive to the notion of a well-behaved space, so to speak. It's called a sober space. So a topological space is sober if for any open subsets such that it does not coincide with S, and if an intersection of two open subsets is a subset of P, this implies that either U is a subset of P or V is a subset of P. Well, that basically means that P defines proper prime ideal in the monoid of open subsets. Then the space is called sober if there exists a unique point inside of S such that P can be represented as a complement of the closure of this point. This might seem a bit strange because we're used to the fact that closures of points are necessarily, they necessarily coincide with the point itself, at least when we're working in a Hausdorff setting. But in general, it's not necessarily the case. So, for example, obviously in the risky topology, it's quite common to have closures of points being some sub-varieties of or sub-schemes or scheme. So this formalism takes care of this situation as well. So we have an alternative formulation of a sobriety of a space. So assume that we have a closed subset. Then we say that it is irreducible if it does not split as a union of two non-empty closed subsets. So once again, topologically, in the sense of the usual, I don't know, spaces that we encounter in algebraic topology, this looks somewhat strange because obviously we don't have too many reducible subsets. But if we're working in the risky topology, a subset is reducible basically when it can't be represented as, I don't know, well, very roughly speaking, as a union of two subvarieties. So you can have something like this. This is obviously reducible. Or you can have, I don't know, some smooth curve, for example, in a plane, and it will be irreducible. So once again, this is just an illustration of the fact that the language of localic topology is more flexible than the language of standard point set topology, because it is equally well adapted to handling stuff like the risky topology or the usual topology where we have closed points and, I don't know, well, CW complexes and stuff like that. So in terms of reducibility, we have this formulation of sobriety of a space. So a space is sober if and only if for any reducible subset in S, there exists a unique point for which F is a closure. So basically the idea of sobriety is that the space has enough points. We have enough points to separate open subsets from one another. Because as per usual philosophy here, we sort of study our space by mapping some test objects into it. In this case, test objects are points, and we just require that this information about points is sufficient to separate different open subsets. And that's an idea that can be generalized further. So I don't think that we'll discuss it in detail today, but the same notion can be formulated for an arbitrary topos. So obviously we can define what is topos of a point. That's just a category of sets. And then an abstract topos has enough points if basically the same thing holds. So we have these morphisms, geometric morphisms between topoi. We consider morphisms from the point topoi, and then we say that a topos has enough points if a collection of all morphisms from the point topoi is sufficient to, well, distinguish morphisms in this topos, something like that. But that was just some tangent, which is not quite relevant to this situation that we have here. So let's prove this intuitively clear idea that if we have a Hausdorff space, then it's necessarily solved. So assume that we have a point in our space, which is T0 plus T2, meaning that it's Hausdorff. Then we can map it into its closure. So let's denote such a map by J, a closure operator. Then S is sober if and only if J is a bijection. By T0, J is an injection. So T0 says that two distinct points have some open neighborhoods such that one neighborhood does not contain, so the neighborhood of the first point does not contain the second point and vice versa. Okay. So by T0, J is an injection. If we take a closure of a point, we necessarily obtain something distinct for distinct points. But also, if the space is Hausdorff, the closure of a point is actually the point itself. So I guess formally it can be shown like this. So assume that we have an irreducible subset that contains 2 points. Then we can use these non-intersecting neighborhoods that exist by the axiom T2 to split F into the union of 2 closed subsets, each of which is non-empty. Okay, and this contradicts irreducibility, and obviously a closure of a point should be reducible by assumption that it is a minimal closed blah blah blah. So yeah, quite a trivial statement from general topology. So now we arrive to a functor which associates to a locale a topological space. So obviously we want to be able to relate topological spaces to locales, even though locales are in principle more general than topological spaces. It still would be nice to have a bridge between them. So we have obviously a construction of a locale from a topological space, but actually we can go in the opposite direction, and it's done in quite an expectable way. We just take the set of points of a locale and then we topologize it. So we take points and we say that this PT of X is naturally a topological space where the pose set of open subsets, the frame of open subsets, is given by this construction. So we just take the collections of these PTs of U, where U are elements of O of X, and PT of U consists of points of X such that the pre-image of U under this point is 1. So this looks a bit funny, but actually all that this says is that it should contain precisely those points which are contained in U. So this condition that P minus 1 of U is equal to 1 basically means that P is inside of U. So we can think of these points as sort of characteristic functions which say to each open subsets associate the information, does this point belong to this open subset or not? And then we take precisely those points which have value 1 on this open subset, meaning that they belong to this open subset. So it's not strictly formal, but that's the intuition. And the fact that this thing is indeed a topology on our set of points of a locale follows directly from axioms of a frame. So this condition about unions and intersections just follows from abstract axioms of a frame. Okay. So now we arrive to an injunction between locales and topological spaces. So in one direction, we take the associated locale of a topological space, and in the other direction, we take the topological space of points on a locale. And why we obtain an adjunction? Well, let me sketch the proof. So assume that we have a topological space, assume that we have a locale. Then to a morphism from a topological space to the space of points of a locale, we can associate a map from locale of S to locale X using the following construction. So if we have a morphism between topological spaces, then we can associate to it a morphism on frames. And then, well, we do this in the following way. So F minus 1 of V, where V is an open subset, well, an element of this frame, consists precisely of those points which send V to 1 if we apply G. So, moment. Yeah. That was just stupid, okay. Yeah, okay. So yeah, so now it makes sense, I guess. Yeah, I guess it does make sense. So yeah, if we have a morphism of topological spaces, then we can associate to each well, then we can associate to an element of the frame O of X, an element of the frame O of S, where we just take the pre-image of this open subset here under the map G, and this works. Yeah. Now it makes sense. I just had a typo here. Okay, so this is correspondence in one direction, and in the opposite direction, we do it as follows. So assume that we have a morphism from the locale or topological space into an abstract locale X. Then we can associate to it a G, which works like this. So we take a point S in S large, and we map it to a point of a locale which works like this. So a point, as we remember, is just a sort of a characteristic function on elements of the corresponding frame. And it says that the value of this characteristic function on V is 1 if and only if S belongs to the preimage of if S belongs to the preimage of V under this morphism. So obviously we have, if we have this morphism, then we have this preimage map, which just takes O of X and maps it into O of S. So it makes sense. Okay. Okay, so we have this, well, I didn't prove that there's an injunction, but I guess it won't be very illuminating. It's better, I think, to try to do it oneself, because it's just a very big, well, not, it's just an exercise in verifying that, well, we have everything that we need. So all morphisms are mapped accordingly. Okay, so actually the property of a space being sober translates to the fact that on this space, the unit of this adjunction, consisting of the space of points and the associated locale, is a homeomorphism of topological spaces. So the unit of this adjunction works like this. So we take a point, just regular point, and we associate to it the corresponding point and side of the set of points of this locale which corresponds to S. So basically how it works, well, the locale which corresponds to S is just the locale of open subsets in S, and then we can consider S as a characteristic function once again, and we just say that the value is 1 when S belongs to some open subset and is 0 otherwise. And so we have the following proposition that the following conditions are equivalent for the topological space. So S is sober, have a homeomorphism, and S is homeomorphic to topological space of points for some locale. So that's one proposition. Once again, the proof is not very illuminating. It's just a tedious verification of the fact that, you know, all adjunctions work. All adjunctions work basically. And we have the dual notion of spatiality. Well, saying that locale is spatial, like a space. It means that basically that in a sense, well, not in a sense, so a locale has enough points if, as I said, I went on this tangent about topoi and having enough points, and that's precisely it for this particular example of a locale. So we say that this spatial if the collection of all points of this locale is conservative, meaning that two open subsets, well, two elements of the corresponding frame, are the same if and only if for any point of this locale, the pullback of this open subset of this element coincides with the pullback of the other element. So basically, we can always tell by looking at the points of this locale, are their elements the same or are they different? That's the idea. And we have a dual proposition which states that for a locale X, the following conditions are equivalent. So one is that it has enough points. The second one is that the co-unit of the adjunction is an isomorphism of locale. And the final one states that this locale comes from some topological space. So clearly, we can restrict this adjunction to an equivalence of categories between sober spaces and spatial locales. That's well, the idea of correspondence of appropriate topological spaces, reasonable enough topological spaces, and reasonable enough locales. In a sense, they're reasonable enough, although we obviously can consider some other examples, and they can be useful in some situations as well. They're just not spatial. Okay, but actually, this duality between spaces and locales can be formalized using some general machinery of category theory, which, as it turns out, explains many dualities involving topological spaces and some algebraic objects. So assume that we have the following situation. So we have two categories over sets and an adjunction between, well, a contravariant adjunction. So it's an adjunction that goes from C to D op and from D op to C. And assume that the composition of elements of this adjunction, so this diagram is not necessarily commutative, I just decided to draw everything together. Don't think that it's commutative. So assume that the functor, which is obtained by composition of S and U, is representable by some object B in D. And similarly, that the functor, which is obtained if we go in this direction, is also representable by some object A in C. Then we basically, and that phi and psi are the representing elements of the value on this functor on on B. So the representing element means that just corresponds to the identity morphism between B and B or A and A. So basically any other element can be obtained by a pullback from this one. Then we say that basically we have dualizing object in this situation. So the dualizing object is this pair A, B, and omega, where A and B are as before, and omega is an isomorphism which is obtained as a composite of this chain. So we start from the value on this A, then we apply the co-unit. So we map the unit. So we map from the identity functor into the composite of two adjoints. and then we apply U as well. Then we have an isomorphism with this set by assumption. Then we have an isomorphism with this set, and also by assumption. And then we have finally an isomorphism with this. So as a result, the idea is that basically A and B are the same object, but in a different categories. So we have something, so the notion of this dualizing object is that we have two different objects in different categories, but they are basically the same. So a situation where this is commonly used is when U and V are embedded. So for example, if we have concrete categories, then it makes this notion of having the same object precise. So we have a set and we have two different structures which relate nicely to one another. So this relationship is expressed by this adjunction. And that's the idea of a dualizing object in this general context. Then, if we have such a dualizing object, then we can represent this adjunction by, by taking this. So, it's not precisely representing the adjunction itself, it's more like representing the result of this adjunction in the category of sets. But if we have concrete categories, for example, and all our examples will be concrete, then it is sufficient to know how this adjunction works in sets to know that, I don't know, for example, we have a natural isomorphism. And as it turns out, several dualities can be expressed in terms of dualizing objects. So, for example, the duality between topological spaces and the opposite category of frames can be expressed like this. So we take a two-point set and we endow it with two different structures. So one of them is a structure of a Sierpinski space where we have one closed point, and sorry, we have one open point and one closed point, right? And the other one is the structure of this terminal local or initial frame, whatever you want to call this. And then using this construction of a dualizing object, we obtain the duality between topological spaces and frames. And as it turns out, this also explains how the other two, not only them, but I restricted to these two examples. So Pontryagin duality, which is a duality between discrete groups and compact Hausdorff abelian groups, works like this. We consider the circle and we endow it with two different structures. So on one hand, a circle is a discrete group, and on the other, a circle is a compact Hausdorff abelian group. And as it turns out, we can use this dualizing object to obtain Pontryagin duality. And similarly, we can use the dualizing object of complex numbers to obtain the Gelfand-Naimark duality between complex algebras and compactly generated Hausdorff spaces. So on one hand, C is a complex algebra, and on the other hand, it is a compactly generated Hausdorff space. Okay, so the final thing that I wanted to cover today was the notion of a localic topoi. So in a sense, a localic topoi is a very simple kind of localic topoi are a very simple kind of topoi. So first of all, any local is naturally a site. because the coverage is given just by the version of the usual open cover topology, because we say that a family of morphisms in X is covering for an object U precisely when the join of elements of this covering family coincides with U. So for topological spaces, this reproduces the usual open cover topology. Then we say that the Grothendieck topos, so Grothendieck topos is just a topos of sheaves on some small site. Is localic if it is equivalent to category of sheaves on a locale. So in a sense, just a category of sheaves on a topological space. And we have the following baby Gero version of Gero's theorem, but for localic topoi. So for a Grothendieck topos E, the following conditions are equivalent. So one, E is localic, so in the sense of the previous definition. The other, it is a sheaf on some category of sheaves on some site which has a structure of a pose set. So in a sense, this explains that there are no not exactly. No, I don't think that I want to go there. I just wanted to say something about possible Grothendieck topologies on pose sets, but I guess that's a talk for it's a topic for another time. They are all very simple, but I don't think that it is really related to what I'm saying here. Okay, so the second condition says that E can be represented as a sheaf topos on some pose set site, and the final condition says that E is generated by subobjects of the terminal object. Generated means that it's it's sufficient to generate under small limits. And assuming the big Gero's theorem, we can actually prove this result. So the first implication is trivial because obviously any locale is a pose set, naturally. Then the implication from 2 to 3. So if we have a sheaf on a pose set, then E is generated by subobjects of the terminal object. Well, if it is a category of sheaves on a pose set, then let's denote by AY the composite of the Ionada embedding into pre-sheaves and then the sheafification functor from pre-sheaves to sheaves. I'm sorry, I didn't explain how this works, but you can just think of it as a sheafification functor from algebraic geometry, algebraic topology. The only important thing about sheafification functor is it's left exact. That's the only property that we really need. And by definition, well, almost by definition, morphisms from images of objects in P under the Ionada embedding into the terminal object are monic. And since the sheafification functor is left exact, it preserves monic morphisms. Well, now we know that the sheaf category is generated by, well, even a pre-sheaf category is generated by the image of the Ionada embedding under colimits. That's called the co-Ionada lemma. And then when we apply the station factor, we obviously still get the whole category. So this means that the category of subobjects of the terminal object generates the whole topos. And finally, the implication 3-to-1, and here we actually need Gauss theorem in its full generality. So assume that we have a topos E, then, well, the category of subobjects in the terminal object gives a locale. It's a certain statement that I don't want to prove right now, but it is true. You can try to think why this is true. Basically, the idea is that if we have like two subobjects, then we can form their intersection over the terminal object and stuff like that. So the idea is basically that we can use the completeness properties of a topos to take meets and joins of subobjects. Then this locale, or I guess would be appropriate to call it a frame instead of a locale because of this. But actually, Gauss theorem implies that for arbitrary topos, we can take as a site for this topos just this category of subobjects. That's a part of the construction of a site associated to a topos. So if we abstractly have a topos, which I didn't define in any shape or form, but basically you can think of it as a generalized category of sets. Then to recover the sheaf structure, so the structure of a sheaf category of subsite, we need to take subobjects of the terminal object. This is the essence, basically, of the Gauss theorem, that we can explicitly construct a certain site for which this will be the sheaf topos. And so we apply the Gauss theorem, and we see that we obtain precisely a site for this category, and since it was a frame, we obtain the first definition that E is a localic topoi. So yeah, obviously, I said probably something very stupid, but here we of course need the fact that subobjects generate the topos, otherwise it doesn't work. But yeah, if they do, then we can use precisely this category and nothing else to construct the site. Basically for the same reasons that if we take it as a site and these objects generate the full topos, then the image and the unit embedding generates. Well, we can take the image of the unit embedding in the topos which corresponds to this category of subobjects, and since what the image of the unit embedding generates coincides with the whole large topos E, this means that we took the correct site to recover E as a sheaf topos. Yeah. Okay. So I guess I'll stop here for today, but I think that we will continue somewhere along these lines next time. So I guess Monday. Okay. Thank you so much for attending. Let me stop the recording.